What's up logical people, this is Amar. In this video we are going to solve a tricky Google interview puzzle. I must inform you that even if you know this puzzle, you must watch it completely because there's going to be a mind-blowing Google twist in the solution. There are 12 men on an island. 11 weigh exactly the same amount, but one of them is either heavier or lighter than others. There's a seesaw on the island which can be used to find out the odd man. But the catch here is that you can use the seesaw only 3 times. So using the seesaw only 3 times, your task is to find out the odd man, that's a man with different weight. And also find out if the odd man is heavier or lighter. Pause the video and think logically. I'd like to thank Krishna for sharing this tricky puzzle, who usually asks this in the interviews at Intel in the form of 12 balls and 3 weighing. Some interviewers also use 12 marbles or 12 coins. Now let's first solve it in a natural way, then we will see the twist. Let's show the men as circles. Make 3 groups of 4 men and weigh the first group against the second. There are 2 possible outcomes. They balance or they don't. Now here we can use some color coding to save information of each man. In the case 1, all men on the seesaw are balanced, which means they all are normal weight. So we will color them green. The group outside is suspicious to be having the odd man. So let's mark the suspects with yellow circle. In the case 2, where the groups don't balance, if the suspect is lighter, color him light red. And if the suspect is heavier, color him dark red. In the first weighing, it doesn't matter which side weight shifts. Just follow the color coding for heavier and lighter suspects. Since the suspicious man is present on the seesaw, we can color the outside men green as they are normal. So this was the first weighing that gives the 2 possible cases as outcome. Let's analyze case 1 for second weighing. Now, how many of the yellow suspects should we choose for the second weighing? So remember, for the second weighing, neither choose too few objects nor choose too many. Because if you do so, you will end up with more than one suspicious man at the end of all weighing. So stay around the middle. Now, if you take exactly half of the total number of suspects, then you may find out the odd man, but you won't be able to tell with guarantee if he is heavier or lighter. So we must choose the next greater number to the exact half value, which in our case is 3. Now, where to place these 3 suspects? Well, there are only 2 logical ways to place them. And you have to balance them with 3 normal men. And both approaches work just perfectly. I'll proceed with the second one. Now we have 3 possible outcomes. They balance, weight shifts left, or weight shifts right. If they balance, then the odd man is standing outside. And we can color the men on the seesaw green. Now simply weigh the odd man against any normal man for the third weighing, and you will know if the odd man is lighter or heavier. Now let's solve for the second subcase. This tells us that either the suspect on the right is lighter or one of the suspects on the left is heavier. Let's color them accordingly. So perform the third weighing between the 2 heavier suspects. If they balance, then it means they both are normal men and the lighter suspect is the actual odd man. We can say that he is lighter. And if they don't balance, then whichever side goes down has the odd man and the odd man is heavier. Now this third subcase is exactly opposite to the previous one. We have 2 lighter suspects on the left and one heavier suspect on the right. Perform the third weighing between the two lighter suspects. If they balance, they both are normal weight. And the heavier suspect is the actual odd man, and this odd man is heavier. And if they don't balance, then the side that goes up has the odd man, and the odd man is lighter. So case 1 is now resolved. Let's move on to case 2, where the two groups don't balance in the first weighing. Here we have 8 suspects overall. Now, how many of these suspects should we choose for the second weighing? As I said before, neither choose too few objects nor choose too many. Stay around the middle. Exact half is 4, so choose the next number, that's 5. Now, which 5 suspects should we choose? We can choose any 5 of them, because we will always have at least one of each type. I'll proceed with 4 heavier and 1 lighter. But how should we place them? So after the second weighing, we will be having the final weighing. This weighing can have 3 possible outcomes. And each outcome should point to one suspect. Only this way we can solve the problem. So for the final weighing, we can afford to have a maximum of 3 suspects. So eventually, by the end of second weighing, we must not have more than 3 suspects. So a combination like this won't achieve the desired result, because if it shifts left, then at the end of second weighing, we will have 4 suspects. With this principle, you can easily come up with a valid combination. Let's place them as shown. We have 3 possible subcases. They balance, weight shifts left, or weight shifts right. Subcase 2a. If they balance, then the odd man is one of the 3 outside lighter suspects. So in the third weighing, weigh 2 of them against each other. If they balance, then they are normal weight, and the odd man is the remaining outsider, and he is lighter. And if they don't balance, then the side that goes up has the odd man, and the odd man is lighter. Subcase 2b, where the left side goes down and the right side goes up. That means the outsiders are normal. As you can see on the right side, heavier suspects are going upward. That means none of them is an odd man, so they must be normal weight. Same way on the left side, a lighter suspect is going down. That means he is in fact not an odd man. He must be normal weight. And we also have 2 heavier suspects on the left that go down. So we can still call them heavier suspects. The final weighing will decide which one of these 2 heavier suspects is actually the odd man. And now the final subcase. These 2 heavier suspects on the left are going upside. That means they are normal weight. So we are now having 1 lighter suspect that goes up and 2 heavier suspects that go down. Perform the final weighing of the 2 heavier suspects. If they balance, then the lighter suspect is the actual odd man, and hence he is lighter. And if they don't balance, then whichever side goes down has the odd man, and hence the odd man is heavier. The case 2 is also now completely resolved. Google would appreciate your efforts, but wait, they may reject this approach. So let's analyze why this approach is not up to the mark for Google. What if Google asks you the next problem to solve this puzzle with 100 men? And you'd also need to figure out the minimum number of weighing required to identify the odd man. Now, this gets very complicated because there will be so many possible combinations that you'd need to consider in each weighing. To make it even more complex, can you solve it for 10,000 men? The logical approach I explained is still applicable to large number of objects. But of course, you would need several hours or days to figure out the combinations. Now think from Google's perspective. They want a dynamic approach. That means your solution must be highly optimized so that in runtime it should quickly handle any given input value of number of objects. Now first I'll show you the expected optimized answer so that you can feel a huge difference between the two approaches. Then I'll explain how to arrive at this optimized solution. Let's number all the men. I'm going to make 3 weighings in this way. Now all these weighing are unconditional. That means a weighing is independent of the weighing result of its previous weighing. On the left you see a table that represents all possible combinations of weighing outcome. Let's give it a try with some examples. Consider person 7 is the odd man and he is heavier. In that case, our weighing result will look like this. In W1, the weight is shifted to right. In W2, weight is shifted to left, and in W3, both sides are balanced. So if you look up for the combination RL equal in the table, it must point to the correct odd man. As you can see here, person 7 is the odd man and the letter H represents he is heavier. One more example. Suppose the odd man is number 11 and he is lighter. In W1, 11 is outside. So the seesaw is balanced. In W2, 11 is on the right and he is lighter. So the weight is shifted to left. In W3, weight is shifted to right. So if you look up for the combination equal LR in the table, it must point to the correct odd man. As you can see here, person 11 is the odd man and the letter L represents he is lighter. So we have seen that our solution perfectly identifies the odd man along with his weight information based on the 3 weighing outcome. Now let's see how to logically arrive at this solution. A weighing has 3 possible outcomes. It can shift to left, stay in the middle or balance, or shift to the right. The balance sign or equal sign tells that the odd man is not present on the seesaw. He is standing outside. Now let's see how to prepare the table. If we have just one weighing, a weighing has 3 possible outcomes. So here we have only 3 possible weighing results, which we also get mathematically as 3 to the power 1. If we have 2 weighing, then for each value of first weighing, we have 3 possible outcomes for second weighing, which makes a total of 9 possible combinations. In a similar way, if we have 3 weighing, then for each value of the first weighing, we can have the highlighted set of 9 possible outcomes for all next weighing, which makes a total of 27 possible combinations. Just look at the beautiful symmetry of the table. The lower half is exactly opposite or inverse to the upper half. For example, LLL has inverse value of RRR. Similarly, LL equal has an inverse value of RR equal. Now the combination equal 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 would mean that the odd man was not chosen for any of the 3 weighing. He was standing outside all the time. And if that happens, we cannot identify whether he was heavier or lighter. That's why we must choose all men at least for one weighing. So we can eliminate the possibility of equal equal equal. Now we are left with 26 possible weighing combinations. We have 12 men, so there are 24 possible suspicious instances, such as 1 heavier, 1 lighter, 2 heavier, 2 lighter, and so on up to 12 heavier and 12 lighter. Now we can map each combination to one suspicious instance. This way we can guarantee that if a specific combination of weighing outcome occurs, then the odd man is so and so, and we can also say if the odd man is heavier or lighter. Let's see how to map them systematically. Just remember 2 basic rules. Number 1. If you map a combination to the heavier instance, then assign its inverse to the lighter instance of the same man, and vice versa. Rule number 2. A man is suspected to be either heavier or lighter. So in any weighing, the number of L mapped to heavier instances should be equal to number of L mapped to lighter instances. Similarly, the number of R's mapped to heavier instances should be equal to the number of R mapped to lighter instances. And this eventually makes total number of L an even parity number. Same way, we get total number of R equal to an even parity number. Now the mapping can be easily done. We have 24 suspicious instances. There are 26 possible combinations and we need only 24 of them. So we should discard 2 combinations. But which 2 combinations should we discard? Simply align with the 2 basic rules that we saw. Just make sure the 2 combinations you discard are inverse of each other. And after removing them, we should have even numbers of L and R in each weighing. For the sake of simplicity, let's remove the combinations L, L, L and its inverse R, R, R. Now let's first map only the numbers. We can simply assign sequential numbers from 1 to 12. And now assign the same numbers to respective inverse combinations. If we map one heavier to LL equal, then one lighter must be mapped to its inverse combination RR equal. The same way we can map the next combination and its inverse combination. Now we have to be careful here. We must keep this in mind that in each weighing, number of L mapped to heavier instances should be same as number of L mapped to lighter instances. Concentrate on the second weighing column. We have 8 L's, out of which 2 are assigned to heavier instances from the top section. Now we need to assign 2 more L's to heavier instances. Choose any one L from the middle section and one L from the last section and map them to heavier instances, so that from each section we have at least one L. And now we can map the remaining 4 L's to the lighter instances. Now look at the numbers 9, 10, 11, which have the values heavier, lighter, lighter. So their inverse combinations should have the inverted values lighter, heavier, heavier, respectively. Similarly, we have the values for 6, 7 and 8. So we can map their inverted values to the respective inverse combinations. Now in the first weighing, we have 4 L's pointing to heavier. So we can map the remaining L's to lighter and assign the inverse values to their counterparts. Finally, in the third weighing, we have 4 L's pointing to heavier, but only 3 L's pointing to lighter. So the remaining L should point to a lighter value, and its counterpart would have the inverted value. Now we have everything ready for the actual placing of men on the seesaw. We can also group all the heavier instances together and group the lighter instances together. This new table would be easier to place the men on the seesaw. We have 12 men to place. So choose either their 12 heavier instances or 12 lighter instances for placing. If your reference of weighing outcome was heavier side, then choose all heavier instances H. Else, choose all lighter instances L. My reference was the heavier side, as I chose L if the weight shifted left side. That means the left side was heavier. Similarly, I chose R if the right side appeared to be heavier. As my reference is heavier side, I'll use the values under the heading heavier. From our table, in the first weighing, we are going to place 1, 2, 6 and 8 on the left side, and on the right side we are going to place 3, 4, 5 and 7 and place the remaining outside. Similarly, place the men for the second weighing from the second column. And now place them for the third weighing from the third column. Now let's check if we can find the odd man correctly. Take some random outcome of the 3 weighing. So we have W1 shifted to left, W2 balanced, and W3 shifted right. Now search for the combination L equal R in the table, and this belongs to man 5. So the odd man is number 5 and he is lighter because the combination is under the lighter heading. Let's cross-verify on the seesaw by marking the man number 5 with appropriate lighter color. As you can see, our solution perfectly identifies the odd man. And this is what Google is expecting. Now you can easily scale up your approach to any number of men. For example, if there are 100 men, then we would need 5 weighing. Simply prepare the table in a spreadsheet, remove the combination with all equals, and keep only 200 rows in such a way that after removing the required number of rows, each weighing has even number of L and R. Now I'll give you a very small task. What if there are 4 men? How will you prepare the table and do the mapping? You can find the answer at the Google Drive link I have shared in the video description below. If you feel it helped you, you can appreciate my efforts by hitting the like button and sharing it on your social media accounts. I'll wait for your answer in the comment section below. Hope you guys enjoyed. Please like and share the video, and if you're new, please subscribe to my channel and stay updated with a new logic every week. Till then, give a try to these hard Google puzzles. Also check out tricky riddles on my channel Logically Yours.